Okay, for this lecture, I've actually decided to lean into some kind of source material to help everybody go along through this course. And the source material I've chosen is the Catalogue of Spacetimes. And the Catalogue of Spacetimes can be found on the web right here at this address. It's from this archive server. And you can just Google it. Maybe Google Catalogue of Spacetime and Muller or Grave, and see if you can find it. And it'll be sort of a textbook for us in a sense, right? I don't want to just pick a textbook and work through because that's probably what everybody's already done. This is more of a reference material, right? This is it's a reference book. And what it purports to be is a list of all the different solutions to the Einstein equation, which means space-time, right? So that's a catalog of solutions to the Einstein equation. Solutions to G mu nu equals 8 pi t mu nu, which we will talk about eventually. And we'll actually execute a solution of that equation for the Schwarzschild geometry. But this is a catalog of all of them. The Schwarzschild geometry, as difficult as it is actually easy as far as these things go. But there are some much more difficult ones. This book doesn't show you how the solutions were made. This doesn't derive any of these spacetimes. It only shows you the final results, which is kind of interesting. But we might hunt down some other solutions, but we'll definitely go through the Schwarzschild one together. And otherwise, the Catalogue of Spacetime is this nice reference material. Another piece of language you could say here is it's a catalog of metrics, right? Because remember, why are there two I's in my version of metric? Catalog of metrics. Because remember how what we're supposed to be understanding as the basic concept of general relativity, right? We model space-time with a four-dimensional manifold. By the way, look how similar the picture I've always been drawing, this thing here, is to the picture that they use in the reference book. I just noticed that, right? Same idea, right? They have a little more detail in there, but this is sort of the picture I always threw down, right? But we know that space-time is modeled by a manifold, and that manifold will have a metric, right? And that metric is going to be a solution of the Einstein equation, right? So whatever that metric is, its big constraint is it has to solve the Einstein equation, right? And that metric lays down an inner product at every point in space-time, which is attached, and it's the inner product is on the associated tangent space at each of these points in space-time, right? Remember how that worked? TQ, point Q. And the metric is a function of the space-time coordinates. So we have a manifold, we have a metric that satisfies the Einstein equation, and also whatever this metric is, not only does it satisfy the Einstein equation, but it's got to be such that if I pick any one point in space-time, any individual point, I can find a coordinate transformation from x mu to the new coordinate x mu prime, and that coordinate transformation will guarantee that the value of this point I picked, let's say I picked the point S, that g mu prime nu prime evaluated at S is going to equal n or eta mu prime nu prime, meaning that I can always make the metric Lorentzian at any given point in spacetime. And that is assured by the Einstein equivalence principle. That is a statement of the Einstein equivalence principle. Now, for flat space, it's much stronger. If there is no curvature, because one of the solutions of the Einstein equation is, in fact, the metric of flat space-time everywhere being the diagonal, on the diagonal, -1, 1, 1, 1. That means if I lay down a coordinate system, a Cartesian coordinate system, on a flat space-time, the metric this metric here will be a solution of the Einstein equation and will satisfy the Einstein equation, and by default, the Einstein equivalence principle is satisfied because every single point has this metric, right? So it's a constant metric. You change coordinates on the space-time. If it's flat, the metric never changes as long as you're in this Cartesian coordinate system. And that's the way we determine a flat space-time, is if you can take your metric and you can find a coordinate transformation that will make that metric equal to the standard Cartesian coordinate system flat space-time Lorentzian metric, which is -1, 1, 1 on the diagonal. If you can find such a transformation where everywhere in space-time you get this, you have flat space. If you can find a transformation where you can only do it at one point at a time, or I should say actually one line of points at a time, turns out you can do it for more than just one point at a time. You can do it for a line of points. But we'll worry about that later when we talk about geodesics and free-falling reference frame. But at least at one point at a time, but not the whole space at a time, then you have a curved space-time. And then the idea is that curved space-times model the real world. All right, so that's really what we're going with. And the Catalogue of Spacetime has all of these wonderful spacetimes in it. But today, so the idea is that you guys get this, you download it for free, and I mean, it's an academic publication that's freely available. And thank these guys for putting it together because it's really great. So what will we see in this catalog? Well, in the beginning of the catalog, in the early sections, they talk about the basic objects of a metric. And this is going to be a little bit of a guidepost to how our course is going to work. The basic objects of a metric means once you have a metric, right? If you assumed to have a metric on space-time, which is what we're doing, remember we agreed that we were going to start our work assuming the existence of a metric and learning everything we need to learn, and then at the end going back and solving the Einstein equation for a metric, right? But we're going to start with an assumed metric. These are very hard problems. Finding these metrics that work, that solve this, big, hard problem. But when you have a metric, understanding the properties of the space-time once you know the metric, not so hard. And you can answer questions like what are the paths of freely falling bodies in space-time? You can figure that out. Like, you have a star here, and then you have some kind of orbit. You can discover that things will orbit really funny around stars if you know the metric around a dense star. And I say a funny orbit because look at the one I just drew. It kind of loops around and comes back and crosses itself. You can't do that in Newtonian mechanics. No matter how dense this star is, Newtonian mechanics will never predict an orbit that loops and crosses itself. But of course, that's totally doable in general relativity. And in fact, in general relativity, you can even have an orbit that doesn't hit the star, but is still permanently sucked into the star. That can't happen in Newtonian spacetime. If you're freely falling unbound, you will remain unbound and you will depart in some kind of hyperbolic orbit. But in a Schwarzschild spacetime, you can actually be captured. But the point is that these paths, all of these paths, can be calculated once you know the metric for the spacetime around the star. So we're assuming that you've solved all that, you've got this metric, and then you can learn a lot of stuff from it. And but in order to tease apart all that stuff, you need to start. So the way this catalog works is they start with the metric, and then they say, okay, you've got all these things you can build from the metric. The Christoffel symbol of the first kind, and the Christoffel symbol of the second kind. Now, we'll have to decide why we're going to call it a Christoffel symbol, but notice the Christoffel symbol of the second kind looks just like the connection, right? The way I wrote the connection, T, they have nu, lambda. We call this the connection, but they're calling it the Christoffel symbol of the second kind, and there's a reason. It's definitely a connection, right? There's no doubt the Christoffel symbol of the second kind is a connection, and it does exactly what we've already said it does in the first few lectures, talking about fictitious forces, and then in the lecture on manifolds, discussing the covariant derivatives and the notion of parallelism, right? We talked about how to take a vector and find a parallel vector at another point, and how the Christoffel symbol was so critical for that, or how the connection was so critical for that. The Christoffel symbol is a very specific type of connection. And look at what this is, right? Look how this is. This is so cool. The Christoffel symbol, the connection, is a function of the metric, right? Don't worry about how right now, but look, if I know the metric, I can take its derivative with respect to lambda. So g, whoops, well, I better take my thickness down. G, they have rho, nu, comma, lambda. That's meant to mean the partial derivative with respect to lambda of g rho nu, right? Which is partial derivative of g rho nu gx lambda, right? So that's all that means. That's all that means. But notice you can take g rho nu with respect to lambda, g rho lambda with respect to nu, g nu lambda with respect to rho, add 2, subtract 1, then multiply by the inverse metric. Make sure you get all your sums going, right? You're summing over rho. You're not summing over nu, you're just summing over rho. Make sure you do that right. Add it all up, add all these up, and then take these and add up get that Einstein sum right. And when you do all that, you'll end up with one of the components of the Christoffel symbol, right? And so that's interesting, right? This is telling us that we should expect to learn somewhere in this course how the metric itself defines the connection. And remember, the connection told us about parallelism, and it also told us about how paths in space-time are calculated through the geodesic equation. We've done those already. We've not done any examples yet, but we've understood in principle how that should work. But what's important now is you can see right here that we better learn why this is the case. But it's really, really interesting, and it shows you why the metric is so important. The metric actually defines the connection. And when you do that, when you use the metric to define the connection becomes what they call the Christoffel symbols. And it's plural because, of course, there are many of them. There's T0, 0, 0. There's not T, gamma 1, 0, 0, gamma 2, 1, 2, etc., 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 all the way to gamma 3, 3, 3. So each of those are a Christoffel symbol, but the total collection of it is all the Christoffel symbols gathered together make a connection. So that's a little enlightening piece, and it's a guidepost to how we want to learn our material here, which is then they have the Christoffel symbols of the first kind, which are very, very similar. The difference, of course, is entirely this first term here, right? That first term is missing. Well, the 1/2 is there, but the g mu nu, that term is here but not there. So these are related obviously by that expression. Now the problem here, of course, with the notation of these Christoffel symbols and the connection is I've always been very careful to write my connections as mu, nu, lambda, where there's no space. I'm not writing it mu, lambda, nu, lambda. I'm not doing it that way because this implies that the ordering is really, really, really critical because this is not a tensor, right? There's no dx mu tensor product, dx nu tensor product, dx lambda. That is not what we mean, right? This is a non-tensor object. So having this space here, I think, is misleading because it implies that the order is really, really critical. But it's not a tensor object. But then look at this, right? If you look at this, you see that you're kind of raising an index, right? You're taking this row here and you're raising it up there in some weird way, right? Normally, if you did this, and this was a tensor, you would end up with T mu lambda rho like that, right? But you're not. You're not in this case. And also, if you lowered if you use the the regular metric to lower that mu, where would it drop? So the point is, this definition is not the same as raising and lowering indices. That's very important to keep in mind. That the Christoffel symbols of the first kind and the second time, they have a very clear relationship that looks a heck of a lot like raising and lowering indices, but it's not, because this is not a tensor. So you got to kind of memorize this. Anyway, so then there's these other tensors. There's the Riemann tensor. This is about the curvature, right? The curvature of space. We're going to understand how if you have two geodesic paths, two paths of objects falling through space-time, they're going to tend to separate, meaning the distance between these points, the spatial distance between these points, or actually, I should say the space-time interval distance between these 2 points along these paths, it's going to grow, or alternatively, it could shrink, right? If it was, say, going this way, it would be shrinking. It's going that way, it's growing. Doesn't matter. If these are geodesic paths, geodesic, when I say geodesic, or I should say geodesic. When I say geodesic, I mean free fall. Particles that are falling only under the influence of gravity. And when they do that, they follow these critical paths, these geodesic paths that can be determined by the geodesic equation, which we learned about. And the geodesic equation is completely driven by the Christoffel symbols. But now we know the Christoffel symbols are completely driven by the metric. So these geodesic paths are completely driven by the metric. But we know that there's going to be this change. These paths are going to separate, right? In flat space, geodesic paths never, parallel geodesic paths never separate. But in curved space, when they start parallel, they tend to separate. Somehow they tend to either separate or converge. And a measurement of that is driven by the Riemann tensor. And ultimately we'll see how that kind of connects to the idea of tidal forces and things of that nature. But notice the Riemann tensor, it depends on the Christoffel symbol of the second kind, which is the connection. And it depends on this connection's derivative, right? That's what this comma is, right? You see that little comma there? That tells you you're taking a derivative. So it's but regardless, taking a derivative is easy. It still depends on the connection, depends on the Christoffel symbols the second time, which depends on the metric. So this thing depends on the metric. You could actually write this out as a function of the metric if you substituted for each one of these things this guy here. And what a mess. What a mess, because just substituting for, say, this is this three-term object, two-factor and three-term object here, multiplied by that. So that's a three-term object times a three-term object. And then here, you have to take derivatives of those guys, right, and put them in there. So by the time you get that full substitution done, it's a lot of different derivatives of the metric. And notice it'll be the second derivative of the metric, right? Because here you're taking, let's blow it up. This is the derivative of the Christoffel symbol, the first derivative of the Christoffel symbol. But buried in that is the first, so the first derivative of this Christoffel symbol itself has the first derivative of the metric. So ultimately, you're going to have a term that depends on G, P, nu, lambda, and then if you were taking, say, this derivative here, there'd be a sigma in there. That's a second derivative, right? And I'm pretty sure the second derivative is written this way. It's not like comma, comma. I've never seen a comma, comma. So that just means take the derivative here first, and then this derivative. Let me get rid of that comma so you don't think it belongs there. So you have this guy depends on the second derivative of the metric ultimately. First derivative of the Christoffel symbols, but the second derivative of the metric. Then you have other things that you can build out of the metric. You can build the Ricci tensor, which is an important part of the Einstein equation. That's an actual tensor. So this is actually raising and lowering. Well, this is contraction, right? You're contracting on rho and you're contracting on sigma, and you end up with. Well, I'm sorry. You're contracting. Yeah, you are kind of doing that. But what you're doing is you're just raising. Yeah, it's a contraction and a raise is what it is. And you ultimately end up with one contraction right here off of P. So that you're basically taking this guy here, right? And you're contracting mu with rho. When you do that, you end up with something called the Ricci tensor. And then ultimately, the Ricci tensor, that can be contracted on itself, because, right, that's two components, right? So if I have R mu nu, we'll see how we can raise it to R mu nu with a simple index gymnastic lift of the index through the metric tensor. And then we just contract off of these two, and we end up with a special number called R, which is the curvature tensor. I've never heard this word until I saw it in the catalog, the Kretschmann scalar. I've heard of the Ricci scalar, never heard of the Kretschmann scalar, but regardless, it's just the curvature, the scalar curvature. Now, this isn't, obviously I'm just going through this, this isn't meant to be literally a lesson in all this, but this is what the catalog says. Hey, once you have the metric, we're going to talk about these important objects. And this catalog is going to catalog all of these objects for each known metric, right? That's really cool. All right, so what next? There are a few others here. The Weil tensor, I'll say Weil, V-E-Y. My friends who speak German, the W's end up as V's. But the Weil tensor is a function of the curvature tensor with a lowered first index. And then there's some anti-symmetrization going on here. You may remember that notation where we put things in brackets when we anti-symmetrize them. There's a little bit of anti-symmetrization going on with the metric tensor there, and that's another special tensor. The Weil tensor is a very, very interesting object. It's pretty an advanced object. We're not going to need that one for a while. No pun intended. The covariant derivative of the metric is zero. That has to do with a metric that's called metric compatibility. We don't have to worry about that right now. But the covariant derivative of a vector field, they establish here, that's just a definition that you already know from the What is a Tensor lecture. And the covariant derivative of a tensor field, I think I also put that equation down. So those are just reference equations. Ultimately, the Killing equation will be very important to us. We don't need to discuss it now, but it's basically saying the covariant derivative of a vector field, it's a statement of a property. If the covariant derivative of a certain vector field, in this case, I guess this vector field here, right? If the covariant derivative of that vector field satisfies this expression, meaning the covariant derivative mu with respect to v and v with respect to mu, if you add it up and you get 0, you end up with a Killing vector, and that's a very useful thing to know. Every metric has its own collection of Killing vectors, and this has to do with directions in which the metric is constant. We'll talk about that eventually. And then, let's see, section 1.4, local tetrad and initial conditions for geodesic. The natural local tetrad, that has to do with our Einstein equivalence principle. And that's finding a frame of reference where the metric at that point is our famous and ever useful Lorentz flat space metric. If we can find a collection of directions at any point in space where the metric expressed in those directions is this, that's the natural local tetrad. Now, we haven't used the language tetrad yet, but we will, and we'll talk about this when we're ready. It's not too long from now. All right, so every book has a beginning, and the chapter 1 of this book, or this reference book, was a sort of a definition of terms and an explanation of the things that they're going to talk about. So chapter 2 is where the fun begins, and it talks about the spacetimes that solve the Einstein equation. And we can actually dive right in because the first spacetime it talks about is one that we already know a lot about. It's the Minkowski spacetime, which is the flat spacetime. And it's the spacetime of special relativity. And let's just see how the catalog presents this, because we'll learn a lot about what we're after. The first thing, by the way, is you notice that the first thing it does is it says, okay, what coordinate system are we dealing with? The space-time is not the same as the coordinate system. The space-time is the natural structure that models the real world, right? So I've always drawn the space-time like this, and I've thrown down these coordinates because in a very indiscriminate and arbitrary way, because they could be any system. The space-time doesn't care what system you use. So when we cite in a catalog the space-time, what we really mean is we're citing the metric, right? The metric of the space-time is what defines the space-time. So space-time equals metrics. And in order to write down the metric, I have to write down an object, g, mu, nu, as a function of space-time. So I'll say x, where x is the space-time coordinates of the points, right? So in order to write this down, I have to have a basis. Because remember, the way we've learned this, g mu nu, dx mu tensor product dx nu. This requires these two one forms here, these two covectors, they are written in the coordinate representation. So in order to write down this component, to give you a number for this component, I have to have a coordinate system, because the coordinate system will define the covectors, and those covectors will define, will have components that define the metric. Likewise, g mu nu, partial mu, partial nu. By the way, if this doesn't make sense to you, it's part of the prerequisites from my What is a Tensor class regarding the nature of the components. Now we're kind of dealing with just components here, but the point is you need a coordinate system. Otherwise this doesn't make sense. And so it talks about the space-time, which is referring to a metric, and it says that metric for the Minkowski spacetime, which is flat, that flat space-time, if I have Cartesian coordinates, meaning I have four, let me blow this up. I have four real numbers. Each real number is, well, four real numbers. Every point in space-time can now be written as t, x, y, and z. Now, they like to do that in this catalog. They like to sort of use these old, this basic sort of elementary physics engineering notation for the coordinates. So we would have written this as x0, x1, x2, and x3. And in fact, in order to understand the way I'm going to teach it, you're going to have to be able to move between these two really, really smoothly. Because I want to be able to write g mu nu dx mu dx nu. And I want you to see that there's an Einstein summation. You can't do that if every coordinate has its own name. There's no way of creating an Einstein sum. But so you have to understand that this is the pairing. And this is going to happen for every coordinate system we talk about. I'm going to move fluidly between this kind of notation here and whatever convenient set of symbols the catalog uses. Also, the catalog does not set c equal to 1, right? The catalog keeps the c in there as c squared. So from time to time, I'm positive I'm going to get tripped up and confused by that. But you shouldn't be. Remember, actually, perhaps I should put CT here for x0, right? So what I've just done is I've just added that C right there, and my x0 is still going to be in length units, so meters of time. CT would be, CT is meters of time as well, but this now becomes, so at least all of them are the same units this way. But truth be told, I actually though, I better be careful here, right? Because the catalog does not do that. The catalog does not put a C there. The catalog has time in different units from space as far as the point goes. So a point, like a point in space-time, right here, the catalog is going to write as a time on a clock and then a position in space. I want to do it as a position in space and time. And then there's this intermediate place where we say CT, right, or X, Y, and Z, which is a position in space and a position in time. But I throw the C into the coordinate. If you leave the C out of the coordinate, you're going to see that you need to put the C in somewhere, and it'll be in the metric. But let's get to it first. What are they trying to show us here? Well, the first thing they jump on is this thing called the interval, right? ds squared is the space-time interval, and this is how you calculate an infinite piece of space-time interval. But look what they say. The Minkowski metric in Cartesian coordinates reads this. They don't say the Minkowski interval, right? They say the Minkowski metric. So what gives? Well, what gives is that they're leaning on this. They think you know this by heart. And of course, you do, right? So you know that this thing really equals G mu nu dx mu dx nu. And because you know that this thing equals G00 dx0 squared plus G11 dx1 squared plus G22 dx2 squared plus G33 dx3 squared. Now I left out all of the non-diagonal terms. I only have these diagonal terms 0, 0, 1, 1, 2, 2, and 3, 3, because I know they're 0. Because here's a dx0 squared, dx1 squared, dx2 squared, dx3 squared. All the other terms are 0 here in this interval. The point is, the reason they say the Minkowski metric in Cartesian coordinates is this, and then they present you the interval, is because they think you're so smart that you just understand the whole point of showing you the interval is so you can read off the metric. And with this case, the metric is G00 equals minus C squared, G11 equals 1, G22 G22 equals 1, and G33 equals 1, and all the others equal 0, right? So I guess you could say GAB, where A does not equal B, they all equal 0. So that's why that's how you use this thing. When you want to see what the metric is, you've got to read it off the interval. That's how they present it. They don't present it as a list of components of metric of coefficients, which would be nice, and some books do, but not this one. This one leans on the interval. And notice that this is the one that's sort of troubling to me, is that they don't set this equal to 1. Okay, so what do they show next? All Christoffel symbols as well as the Riemann-Enrique tensor vanish identically. So what's important to understand there is the Christoffel symbols are those connection coefficients, right? Mu, alpha, beta that we calculated. And in this coordinate system, only in the Cartesian coordinate system of a flat space-time, will these Christoffel symbols vanish. And they will always vanish because if you go back to the equation we used to calculate them, the partial square of epsilon dx, let's see, beta dx alpha dx gamma. Remember there was this term, there was two factors, right? And this was one of the factors. Well, that's the second derivative of a constant. Well, the first derivative kills it to 0 anyway, but it's a constant. This function, right? This function on space-time, well, that just equals this E beta. That just equals either -1 or 1, depending on the value of beta. And it's a constant. So this derivative is always 0. So every one of these terms is going to be 0. So the Christoffel symbols, which is just another word for the connection, which we calculated in our last lecture using this formula, or using that formula that involved this mixed partial, and then there was another derivative here. That's always going to come up zilch. We're not using, by the way, we're not using the Christoffel symbol definition here. That's something we're going to derive later. This this form, it's going to be ultimately equivalent for these various spacetimes, but remember the connection itself has more to do with the transition between the coordinates. So it's no surprise the Christoffel symbols are 0. Now, the Riemann and Ricci tensors, we haven't studied those yet, but when we do, we'll realize they're related to curvature, and they will vanish identically, not because of the special coordinate system we're in, the Cartesian system, right? Right now, we're in the Cartesian system, and that Cartesian system makes these Christoffel symbols vanish identically. But the Riemann and Ricci tensor, those are going to vanish identically because the space-time is flat. So what that means is that when we change coordinate systems, for example, we go to cylindrical coordinates, we're going to discover these guys may not be 0. They may reemerge. In fact, of course they will. But these will always be 0. These will always be 0. In fact, let's have a quick look at that. Don't worry about this right now, and don't worry about that right now. That has to do with the tetrad system, which we will get to later. But the cylindrical coordinate system is Minkowski space expressed in cylindrical coordinates. So what we have to appreciate now is we have to appreciate that we're starting from the coordinates of a point in the Cartesian system, and we're moving to a point in the cylindrical system. Let me get rid of this x here. I don't know why I have that. So if this is the coordinates of the point in the Cartesian, coordinates of a point in space-time, in Minkowski space-time, in the Cartesian system, and the coordinate of the same point in some curvilinear system, right? So we know that we should be able to write the points in the Cartesian system as a function of the point in the as a function of the coordinates in the curvilinear system, and likewise, we should be able to take a point in the curvilinear system and find its coordinates if we know the point in the Cartesian system, and these are the transition functions, right? Now, with the transition functions, once we have those transition functions, we can then calculate the connection coefficients. And, for example, we could calculate R 5, 5. But in the cylindrical coordinates, you may remember, the z doesn't change, so the transition function is going to be z equals z. So if this is the Cartesian system and this is the cylindrical system, z will equal z. R in the R in the cylindrical system is going to be x squared plus y squared, the square root of x squared plus y squared. Let me erase this. Right, that's the transition function for R. And what else do I need? I need phi. Phi is going to be the arc tangent 2 of y comma x. Arctangent 2 is a fancy arctangent. It's the inverse tangent function, but it returns the correct quadrant depending on the sign of y and the sign of x. It eliminates the ambiguity. It's actually a computer science term, but just think of it as the inverse tangent. It just is a computer. The reason I said arctan 2 is the catalog actually uses it. In an earlier section, the catalog uses this arctan 2. But that is just a function, a special version of the inverse tangent that gets the quadrant right. The problem is there's some ambiguity with y over x, right? The inverse tangent of y over x. Well, y over x is going to have a sign depending on the sign of y and the sign of x. But if y is the one that's less than 0, or if y is greater than 0 and x is less than 0, that puts the resulting angle in a different quadrant than if y is less than 0 and x is greater than 0. So arctan2 figures that out. So instead of putting in just the ratio of y to x, you put in y and x, and arctan2 looks at the signs and things like that. So that's just an important point, but arctan2 is you'll see it in most computer languages. They have arctan2 as the way to calculate the thing. So these are your transition functions. Here's a transition function for phi, for z, and for r, right? And likewise, there's a transition functions going the other way. And from those transition functions, you can calculate Christoffel symbols. But you'll notice that they're not all 0, right? They're not all 0. There's 2 of them that are non-zero. And it's r theta theta, and it's psi r, no, it's r psi psi, or r phi phi, and phi r phi. So in cylindrical coordinates, Minkowski's case in cylindrical coordinates will have this metric, and that means that g00 now is minus c squared, so that's not a big deal. grr, which I would call g11, is simply 1, so that's not a big change. I guess phi phi, which presumably we would call g22, that's going to equal r squared, and gzz, which equals g33. My z's look like my 2's, so I better put little slashes in there. That's going to be 1 again. So this metric is not crazy different than the original metric, but it's not constant in space-time. Right? Now you have to remember that g mu nu is a function on space-time. In particular, it's a function of x2, right? Or g mu nu is a function of r. So if this is the origin of your space-time coordinate system, the farther out you go, the bigger r is, the bigger this g22 term gets. Right? The bigger r is, the bigger the g22 term gets. So in a cylindrical system, it looks like that, with the z-axis coming up like that. Right? So now you have a metric that's not constant on space-time. However, the beauty is you execute one coordinate transformation, right? You take this metric here, you take this space-time, these coordinates, and you just say, you know what? I'm going to convert r back to x and y. I'm going to convert z back to z. I'm going to convert t back to t. And when you do that, the metric will transform itself back into this metric right here. So one transformation will eliminate this r dependence of the metric. That one transformation will eliminate it. And therefore, this is still a flat metric in cylindrical coordinates. Likewise, in spherical coordinates, same story. Spherical coordinates now, you have g00 still c squared. This time part doesn't change much, right? It's only the space part, the way we're laying out our coordinate lines in space. We're not changing the way we lay out our coordinate lines in time. Notice that, only in space. I'm going to change the coordinate time in time in the next lesson, right? The next lesson, we're going to change this one too. But in spherical coordinates now, you still have 1 for the radial, and now for g22, you get r squared, and for g33, you get r squared sine squared theta. So G11 equals 1 and G00 equals minus, well, I'm going to say minus 1. I'm going to just in my own brain make C equal to 1. So this is the metric coefficients from this interval for spherical coordinates. Flat space-time, Minkowski space-time, spherical coordinates, this is the metric. And now, not only is it a function of the radial distance, but the 3,3 component is a function of the radial distance and this longitudinal distance. And in fact, the metric disappears, right, for theta equals to 0. The 3,3 component goes away altogether, right? So the spherical coordinates will have its own transition functions, right? So how will that work? I think it'll be something like x equals r sine theta cosine phi, y equals r sine theta sine phi, z equals r cosine theta, and then t will equal t, right? T is not going to change. So it's actually a problem. I should write like t prime equals t, right? Because we're using t in the spherical coordinates. So if I were to change to these transition, I need a new symbol for the new system. So say t prime. And if these are the transition functions, and likewise there's the inverse versions of those transition functions where r equals x squared plus y squared plus z squared, the square root. What's next? Theta is going to be arc tan 2 of the square root of x squared plus y squared comma z, I think. And phi is arc tan 2 of yz. I'm pretty sure that's it. And then, of course, with that, then also t equals t prime. Sorry about all this stuff. It has to do with the way I screenshotted the book, right? I've gotten all this. It's part of the app, right, that I'm using to read the PDF. So all of this is just a screenshot, artifact of a screenshot. So with these transition functions, right, with these two sets of transition functions, I can, using the formulas we learned from last lesson, calculate these Christoffel symbols. In fact, I think we did one in the last lecture. I think we did this one, actually. We actually calculated that one using these transition functions here. I think we calculated this Christoffel symbol. But there's others that are not 0. If they're not shown here, it's 0. These are only the non-zero Christoffel symbols. And then remember, you saw earlier when I showed you back in the beginning, I showed you that there's a, let me erase this so you can see it. If you look at the Riemann tensor, you'll see that these Christoffel symbols, to calculate the Riemann tensor, you need the derivatives of the Christoffel symbols. Well, interestingly, that's one of the things that they like to do in the catalog. They not only calculate the Christoffel symbols, but they know that it's pretty common for you to need the derivatives. So they provide the derivatives of the Christoffel symbols also, just in case you need them. Because I guess, it's not very hard. Like you could almost see, let's see, theta r theta. Which one is theta r theta? Theta r theta is 1 over r. So theta r theta with respect to r, well, that's not too hard to do, minus 1 over r squared. It's not hard to take derivatives of these things and get these things. Although, you may not remember that the derivative of the cotangent of theta, let's see, phi theta phi, where's that one? Phi theta phi with respect to theta, right? You may not remember that this is the derivative of the cotangent. Anyway, and then again, the local tetrad, that'll be an interesting thing to go through, but it has to do with coming into basically the Einstein equivalence principle frame that has a metric that doesn't look like this. The metric in a different frame looks like the regular Cartesian metric, right? There's a frame of reference where this metric, guaranteed, looks like looks like this, right? And that's what this tetrad thing is all about. This tetrad thing is all about finding that frame of reference, that special frame where the metric is flat and Cartesian. Flat and Cartesian. So that's the spherical coordinates. So notice all we're doing is we're screwing around with coordinate transformations. I'm starting with the flat Cartesian Minkowski metric, and I'm making these kinds of substitutions, and I'm getting the metric and spherical coordinates. I'm just making these transitions all the time, and I'm generating Christoffel symbols because these guys are highly nonlinear in the coordinates, whereas the Cartesian system is completely, the coordinates don't change. There's no change in the direction of any of the coordinates as I move through space-time. But here they do change. And that generates these Christoffel symbols, which generates these fictitious forces that tend to move things along r, or along theta, or along phi in a way that appears to accelerate. But that acceleration is an artifact of the coordinate system, and that is shown by the appearance of these Christoffel symbols. And that's what we talked about in our previous lecture. All right, so now let's look at one where we do again, it's just another coordinate transformation, but we're going to start with the cylindrical coordinates. So the new coordinate system will be called rotating coordinates. And instead of just changing the way we lay down things in space, right, we're going to change how we lay out some things in time. So normally we would have, we're dealing with let me see if I can do it a little cleaner. We're dealing with a polar coordinate system, right? So we have basically our polar coordinate system with r, and I guess in this case it's phi, right? And we also have theta, which I'm suppressing, because I guess this theta would be the angle coming with this thing out of the whiteboard. There's an angle off of that axis right out of the board, and that would be theta. So we're suppressing that, and of course we're suppressing time. But now what we're going to do is we're going to make an arbitrary coordinate. We can make any coordinate transformation we want. And in this case, the one we're going to make is we're going to say that in the new system, I guess we'll call it all the prime system. First of all, t prime will equal t, and r prime will equal r, and theta prime will equal theta, and phi prime will equal phi plus omega t. So this is a completely arbitrary coordinate transformation. First of all, notice that the coordinate system we're starting in is already the polar system, meaning the unprimed coordinates is the polar system. The prime coordinates is very close to the polar system except for this last coordinate, which is the transformation is that the phi coordinate in the new system is equal to the phi coordinate in the old system plus a certain constant, omega, times the time in the old system. So it's actually a function of 2 of the old coordinates, which is fine because that would mean phi prime the new coordinate phi prime is a function of the old coordinates t, r, theta, and phi. Now, the way we really want to write this is x mu prime is a function of x mu, right? That's my notation, my favorite notation. I like to put the new coordinates, give it a prime, but I put a prime on the index, right? An alternative way of writing it is x, say, hat mu is a function of x nu, right? The new coordinates are the hatted ones. The old coordinates are the unhatted ones. This is my favorite. This is my favorite. The point is that the implication is that what we're doing is we're rotating the coordinate system. The axis that defines phi is actually rotating with a speed, with an angular velocity, omega. So omega has to be in units of angle per time. Now notice that in this case, it's pretty clear, time is measured in seconds, so it would be angle per seconds, because remember, they have their C not set to be 1. But if C was set to be 1, it's no problem, right? It's still no problem. It's just the angular velocity would now be, instead of radians per second, it would be radians per meter, where meter is the measure of time, right? So, because C equals 1. So we're not, just keep that in mind. It's just the units are all that matters. And notice the way this is done, by the way, doesn't matter, because whether time is seconds or not, that transformation is going to be just t prime equals t, whether t is measured in meters or seconds. Here, the significance is you got to get the right units for your angular velocity, right? But anyway, so you're going to make this transformation. But so everything is the same. dt prime equals dt, dr prime equals dr. Let me erase this. d theta prime equals d theta, and d phi prime equals d phi plus omega dt, right? So now we can make this substitution, right? This substitution right into our spherical coordinate system. That means we're starting with this metric here. Let me make my thickness back up again. We're starting with this metric right here, right? And we're making a coordinate change. We're making a coordinate change by changing this coordinate according to d phi prime equals d phi plus omega dt. So the way we write this is d phi equals d phi prime minus omega dt prime, because we know dt goes to dt, so I can solve this thing for d phi, right? And I can put that up in here. And so I can now take this and just transform it straight out, meaning I make this substitution for d phi, and for dt, I just make the substitution dt prime. Same with dr, just make that dr prime. And same with d theta, make it d theta prime. And those don't even, those don't change, right? Those have, there's no coefficients, there's no functional relationship. It's just literal. It's an identity transformation for everything except this last one, right? So if I did that and I made that substitution, I'm going to end up with this metric here, right? And notice how quickly these metrics get to be a mess, right? First of all, when you look at this metric, what are you going to see? Well, they felt the need to simplify this term and combine the dt and the d phi together, right? Actually, the way we're talking about it, these would all have little primes on it, right? Because we're talking about transitioning. Oh, you know what? They're doing this in cylindrical coordinates. Sorry, that'll be dz. Yeah, of course, it's rotating in cylindrical coordinates. You don't need to have a theta. You're just having a z. So this will be z and z prime. And when I went back here, spherical, I should have gone all the way back here to this cylindrical coordinates, right? So we're just going to substitute right into there. D phi equals d phi prime minus omega dt prime. And that's going to get substituted right in there. And then these others are going to go dz equals dz prime, dt will go to dt prime, dr will go to dr prime, right? So let me see, make sure that'll be z, and that doesn't exist. That's just a z. It's even easier to understand. But when you make that substitution, even a simple substitution like that, it gets to be kind of a mess. And you end up, they felt the need to combine these to, because they could factor it together, so they made a single square. Okay, there's this weird factor here in front of the d phi, so now this would be g, I guess that's 2, 2, right, because x2 is probably phi, the way we're going to map it. So g22 is now r squared over 1 minus omega squared r squared c squared, which would be nice to have c equal to 1, then you wouldn't have that term, right? But it's not the way they do it. So here you have g22 as a function of r again, but it's no longer just a function of r squared or just r. It's actually, well, it's usually r. It's not r squared anymore. It's now r squared over, some combination of things that could be positive or negative, right? I mean, this term here is always going to be positive, and so r is big enough, g22 is going to go negative at some point. So that's kind of a mess. And then, but that's not, you see, that the problem with that is that's really not g22, right? Because there's a d phi squared term in here, right? It's this product, this thing, times that, plus that, right? So g22 is really those combinations. So you can't even, they've put it in a way where you can't even read off the metric very well. So I don't know if I like that, but I'm not quite sure why they did that, but they did that. So very well. I mean, there's a reason, right? And here, this thing here, actually this term here is going to cancel that term here for the front end of this, leaving this and that together. I'm not sure why they did it that way, but they definitely combined a bunch of stuff. So you're going to have to hunt and peck for your G22, because it's this plus some other term that gets pulled out of here. But what is important, and maybe this is why they did it, they're concealing a mixed term, because this is going to have a term that looks like 2c minus 2c omega r dt prime d phi prime. So there's actually an off-diagonal element term in the metric. So when you write down this metric, you're now going to have a G00, a G11, a G12, oops, a G22, a G33, and you're going to have a G12 or G02 and a G20, and then the rest of these will be 0, like that. So you now have off-diagonal terms, and I don't like to say off-diagonal because it implies that the metric is some kind of matrix, and it's not. This is just a bookkeeping system, just an organizational system, so I can quickly find G, alpha, beta by just looking it up on a table. I'm missing something. Oh, yeah. But this transformation, that's what it's done. It's driven an off-diagonal term. So even if you have off-diagonal terms, this thing can still, through a simple transformation, go back to n alpha beta, which is minus 1, 1, 1, 1, the Cartesian system, flat spacetime. We're one transformation away. And it is not obvious. If you started with this thing, don't tell me that you could look at this and say, oh, yeah, this is obviously flat space. This is still Minkowski flat space. It's just the reference frame is spinning. That's really what it's all about. So how would you recognize that to be flat space? You would have, if you started from this and you had to come up with a coordinate transformation to get you back to this in order to prove it was flat space, you'd be in big trouble. So the way you actually do it is you actually take this, you extract the metric tensor. Here they actually did list out the metric tensor components, by the way. Oh, and you know why? You know why they did it? The reason they listed out the metric tensor components was exactly for the reason I showed you before. This metric element, this line element, hides the true components, right? I almost miscalculated by just jumping on this, forgetting that there's a squared term right here, right? I just jumped on this, and I forgot there was a squared term in here, right? So my calculation of G22 was all screwed up. And they realized that. For some reason, they just love this line element form, and therefore they realized, well, we better actually write out the components so people don't mess around. But look, G phi phi, it's actually just r squared. And of course it is, right? Because this cancels with that, leaving r squared omega and r squared omega, and then it's r squared omega over c, then plus this. That's going to all work out, evidently, to get you that. All right, fair enough. But the others, you can see these two are obvious. These two you can read right off without any trouble. The gt phi omega r squared, what did I call it? Yeah, so if you calculate this out, right, you're going to get omega r squared, and then GTT is this thing here. So so now they actually list out the metric tensor because you can't just extract it straight from the line element. Anyway, but my point is in order to see that this is flat space and that this is flat space, what you're going to have to do is you're going to have to calculate the curvature tensor, mu, alpha, beta, gamma. And what we'll see is that if you calculate this curvature tensor and all the components equal 0, then you know that you're dealing with flat space in some kind of weird form. All right, so that's pretty good. I think we've made some real good progress today. We've jumped on the Catalogue of Spacetimes. I've sort of introduced it as like a point of departure for this course. I've decided that that's the point of departure we'll use. And then we've reviewed and talked about flat space in several different coordinate systems. And these are familiar coordinate systems with the possible exception of the rotating system. But if you did classical mechanics, you've done some work with a rotating coordinate system. But now we've talked about it in terms of the metric and the transformation of the metric. And remember, we always started with this metric, and then we took the transformation equations and we got this metric. And we took then we took this metric again and took the transformation equations for spherical coordinates, and we got this metric. Then we took this metric and we decided to take another transformation on this metric to get this metric. And all these things are just one transformation after another, and they're arbitrary, right? I could have said d phi omega dt plus gamma d theta, some crazy coordinate transformation that has no particular meaning except it just came to my head. And then I'd get another metric, but it's still fine because there's no restriction on how I can do that. I'm allowed to take any kind of transformation I want, and it will always end up with a metric that is equivalent. It's always a transformation away from the flat Cartesian Minkowski metric. Now, on my next lesson, we're going to do this one more time in a very counterintuitive but very useful way. And I'm going to show you how we can take the Minkowski flat metric, this Minkowski spacetime metric here, and what we're going to do is we're going to compactify it. We're going to, instead of making it all real numbers, we're going to put it in a finite region of the plane. And that is going to be a very helpful thing down the road, but it'll also just get you loose with the idea of radical coordinate transformations, indiscriminate, radical, wild coordinate transformations. That's the way it's going to look to us, of course, because we haven't studied this subject all our lives, but it took many, many years for people to figure out the best transformations to use and why. It's a lot like topology, right? Topology was around for decades before someone finally figured out the best way to define open sets and things of that nature. Likewise, these coordinate transformations came about after a lot of thinking, and so, but I want you to understand that they are quite arbitrary, and they can be used in a very, very flexible and powerful way. So we'll do one more lesson like this, but we're going to get away from the standard the standard coordinate transformations, Cartesian to cylindrical to spherical, and even these rotatings are pretty standard. And we're going to do something that's very, very strange and flexible that's going to have the intent of taking all of these variables of Minkowski's coordinate, all these coordinates from the entire real line down to a limited amount of space. And I think that's a good exercise to do next, even though it's a little out of order for the non-standard course, because it really starts giving you flexibility and understanding how arbitrary and important these coordinate changes are. It also talks a lot about the time coordinate, which confuses a lot of people, and it shows how coordinate time can be this just arbitrary, wacky number. Because even here in all these, this time, right, is the actual time of somebody, right? This, you know, you just lay down cylindrical coordinates, you have a lab clock, and you measure time. And in the spherical coordinates, all you've done is thrown the time on, so that's not a problem at all. And even in the rotating coordinates, you're tracking time. Your time coordinate really doesn't change, right? Whereas the GTT, right? The time coordinate is still just the coordinate time on somebody's clock. And so now we're going to go into things next week that are the time coordinate becomes a little bit more counter or non-intuitive. All right, so we'll see you next week.